Many times when you're dealing with the ideal gas equation, you will end up under what are called standard conditions. So basically the scientist said, hey, let's make a condition where the temperature and the pressure aren't going to change. Okay, and when that happens, you're under what's called standard temperature and pressure. Many times they just abbreviate it with STP. So if they say a gas at STP, you have to know that means standard temperature and pressure, which means that anytime you're at STP, the temperature must be 0 Celsius or 273 Kelvin, and the pressure is 1 atmosphere. Okay, I'm looking at the equation sheet right here under gases. They do have STP equals, oh, they did change it. They did put, it's not 273, it's 273.15. It used to just say 273. Doesn't matter, your math isn't going to change with that 0.15 right here. So STP equals 273.15 Kelvin and 1.0 atmospheres. So that is something that is on the equation sheet. Okay, so we can substitute those values into the ideal gas equation, and we can use PV equals nRT. So in this case, we know R because it's always the gas constant. The temperature is a constant. It's the 273.15. The pressure is 1 atmosphere. And then if you have a mole of a gas, and that means any gas, helium, carbon dioxide, it doesn't matter. If you have 1 mole of any gas and you plug all those numbers in, you plug in 1, you plug in 0.08206, 273, and 1, and then and solve for volume, what you'll find is that 1 mole, again, of any gas at STP has a volume of 22.4 liters. Okay, and again, that is also on the equation sheet here. The equation sheet says ideal gas at STP equals 22.4 liters per mole. Okay, and that's a conversion that you can use. Instead of using a whole ideal gas equation, you can just know that anytime you have 1 mole, that gas is going to occupy a volume of 22.4 liters. What if you have 2 moles? Well, then obviously, you're going to double that, 44.8 liters. Okay, so however many moles you have, you can use that conversion. 1 mole equals 22.4 liters to do that. Okay, so here's another example. A hydrocarbon with an empirical formula of CH2 has a density of 1.8 at 0 degrees Celsius and 1 atmosphere. So you are at STP. A possible formula for the hydrocarbon is, so anytime they ask about the chemical formula, you need to know the molar mass. So the molar mass, remember, is the dirty P equation, so dRT over P. So the density is 1.88 grams per liter. R is 0.08206 liters atmospheres over Kelvin mole. Notice how I do those units there. The temperature is 273 Kelvin, and the pressure is 1 atm. And again, let's check and make sure. Liters and liters, atmospheres, atmospheres, Kelvin, Kelvin. Notice what we have left. Grams on the top, moles on the bottom. Okay, so now we're going to take 1.88. We're going to multiply. This is the part right here. If you look at this right here, that's the part that actually equals 22.4 in your calculator. If you just type in 0.08206 times 273 and then divide by 1 or not, it's 22.4. So really what we're doing here is we're taking 1.88 and we're multiplying by 22.4 equals 42, roughly. So CH2 has a mass of 14, and 14 times what number equals 42 is 3. So that means we've got to take CH2 and multiply it by 3. So that's C3H6 is the correct response. Okay, and then we talked about this earlier, but again, we can use the ideal gas equation to get Boyle's law, Charles' law, the combined gas law, etc. Anytime something is constant, you can remove it. Okay. Anytime you're comparing, let me clarify that. Anytime something is the one thing is the same from one side to the other. Okay, so something has to be changing. The pressure was this, now it's this. The volume was this, now it's this. You have to use some form of the combined gas law. Okay, So when something is constant, like R, but some other things are changing, temperature's changing, volume's changing, pressure's changing, that means that, again, those are the things you can remove, and the only things that are changing in this case are the pressure and the volume, or the pressure and the temperature, or the volume and the temperature, okay? So let's look at an example of this scenario, okay? So a 0.10 mole sample of gas L, some made-up gas, is placed in a rigid container at 400 Kelvin and 0.25 atmospheres. When more moles of compound L are added, so the moles, that means the moles are going up, the pressure increases to 0.75 atmospheres at 400 Kelvin. The temperature hasn't changed, obviously. Determine the number of moles of L now present in the container. Okay, so here's one where really think about PV equals nRT and what things are staying constant. Okay, 400 Kelvin, 400 Kelvin. That means the temperature is staying constant. Are the number of moles staying constant? It was 0.10, but now it says more moles are added, so no. Okay, R is staying constant because it's always constant. And it does say a rigid container. That means the volume is constant. Okay, and so now it's like, now we basically want to get to this point right here where you've got to get them both on the same side of the equation. So that means pressure, notice to get n to this side, we have to divide it. So pressure over moles is a constant. Wait, but there's no law for that. You're right. It's not Charles' law. It's not Boyle's law. It's just whatever. It can be any of those four variables, any version of pressure, volume, temperature, or moles. So that means we can say that P1, just like up here, we went from PV equals a constant to this. So P1 over N1 equals P2 over N2. So the initial pressure is 0.25. So 0.25 over the initial number of moles, 0.10. The final pressure is 0.75, and then our final number of moles is what we're looking for. Now we have to cross multiply, and we have to divide. So I'm going to cross multiply this way. So 0.75 times 0.10. And then I'm going to cross multiply this way and then divide by 0.25. So divide by 0.25 equals, and you probably could have done this in your head. I'm just trying to show you the math. But N2 is, this goes up by a factor of 3. Oh, then this is going to go up by a factor of 3.3. Okay? So any different version of that ideal gas equation, when one thing changes to something else, start with the ideal gas equation, eliminate things that are constant, and then set it by itself, and then set them equal to each other, the initial versus the final conditions. Okay, the last thing we're going to talk about today is, oh boy, a bunch of exams. So yeah, we're going to stop there. Okay, it's not accounting. Remember with the kinetic molecular theory, there's two things that we considered. To be an ideal gas, we, again, pretend like or act as if the gases don't take up any space and they aren't attracted to each other. Okay, so the first one we're going to talk about is that gases don't take up any space. Again, to be an ideal gas, we assume the gases don't take up any space. But again, in reality, they do take up a little bit of space. Okay? What space do they take up? They take up the space where the gas actually is. The gases aren't made up of nothing. The gases do take up some of the space. So when you have a container that's 5 liters, you don't actually have 5 liters of free empty space because the gas particles are taking up a little tiny bit of that. Okay? So the actual volume, so the real volume, is greater than the volume used with the ideal gas equation, because again, when we say volume, we mean the volume of the gas. Okay, the actual gas volume, not the container volume, the gas volume is greater than the volume used with the ideal gas equation, because again, we assume that the gas volume is 0. Okay, because there is no factor for volume in the ideal gas equation. Okay, there's the container volume in the ideal gas equation, but there's no how much space do the molecules take up. There's no factor for molecular volume. Okay, So what does that mean? So since we don't account for molecular volume, the pressure of the gas is going to be greater than expected. Okay, well, let's think about this mathematically. P equals nRT over V. We say a 5-liter container. Again, this is the volume of the container, not the gases. Is the volume actually 5 liters? It's not. What is it? Is it bigger than 5 liters or less than 5 liters? It's less than 5 liters because, again, some of the gases do take up some of that space. Okay, so the gases actually do take up a little bit of the space in the container. So what is this number really? It's actually a little bit smaller than 5 liters or 2 liters or whatever the number happens to be. So the smaller the denominator gets, the bigger your answer becomes. So since the actual volume, not the ideal volume, the actual volume is a little bit smaller than whatever number we're using, again, the actual pressure of the gas, so that's kind of saying the real pressure of the gas is greater than what you would expect it to be under the ideal gas equation. Okay? The real volume is less than the number we use in the ideal gas equation, so the real pressure is greater. Okay? So, in summary, the actual or real gas volume and pressure, again, real gas volume, again, it's kind of confusing there because there's this volume, that's the volume of the container, okay, and then there's the gas volume. The volume that the gas takes up is greater than expected by the ideal gas equation because, again, we don't account for the volume of the molecules in the ideal gas equation. The most confusing part of that to me is the volume of the container versus the volume of the gases. Okay, here's the gases in here. This is the gas volume, whereas this whole thing is the volume of the container. Okay, so the gas volume and the pressure, because again, the volume of the container is lower than it actually is, than we say it is. So the pressure is greater. And again, these are tough questions sometimes. Okay, and again, the other assumption is that molecules are not attracted to each other, even though there is some attraction. Okay, well, what happens if the molecules are attracted to each other? They don't bounce off of each other like perfectly elastic collisions. Okay, what they do is they'll kind of be attracted to each other, and so when they bounce off of each other or don't stick together still, they lose some of that energy, and so what happens is they strike the walls of the container with less force. And when they hit the walls with less force, what does that do? It causes the pressure to be lower. Okay, so when you don't account for molecular attractions, the pressure is lower than expected. So when you don't account for molecular volume, the pressure is greater, right? The pressure is greater than what you would expect. When you don't account for the fact that molecules are attracted to each other, the pressure is less than what you would expect it to be. Okay, let's take a look at a couple of examples of this. It says a vessel contains argon at a high pressure. So high pressure typically means there's a lot of argon in there. There's other things that could make it be at a high pressure, but they don't tell you, so I'm just kind of assuming that there's a lot of argon in there. Which of the following statements best helps to explain why the measured pressure is significantly greater than the pressure calculated under the ideal gas law? So again, what did we say here? We said that when you don't account for molecular volume, the volume of the gas, when we say molecular volume, okay, that's what we're talking about here, is we're talking about the volume of the gas itself. When you don't take that into account, the pressure is higher than what you expect it to be. Okay, is that because the molar mass of argon is large? Nope, that's not what we talked about at all. Is it the fact that argon becomes a diatomic molecule? Well, that would lower the pressure, not raise the pressure. Okay, C, the attractive forces among argon atoms would cause them to collide with the walls of the container with less force, which is true. That is 100% true. But that's not going to make the pressure greater, right? That would make the pressure lower. That's our second one here. That's this. Okay, when you don't account for the attractions, C is absolutely true if the answer was lower. Okay? D, the combined volume of the argon atoms is too large to be negligible compared with the total volume of the container. Because the volume of the atoms is large, it means the free space within the container is actually smaller than what it's supposed to be, And then again, using PV equals nRT and solving for pressure, if that volume of the container, again, volume of the container here, not the volume of the gases, is lower, then the pressure is higher. D is absolutely correct. All right, last one. A 1 liter sample of a pure gas is found to have a lower pressure than that predicted by the ideal gas law. The best explanation for that is, so again, a pure gas is lower pressure. Again, not accounting for volume makes a greater pressure. Not accounting for attractions makes lower pressure. So having a combined volume that is too large to be considered negligible when compared to the volume of the container, again, that would make the pressure higher. Okay, that A and D are pretty much the same answer. Have a low molecular mass, therefore do not strike the walls of the container with as much force as expected. Again, this has nothing to do with molar mass, or I think up here they use molar mass. Yeah, molar mass. Here they call it molecular mass. Same thing, no. Okay, they are attracted to each other and do not exert as much force on the container walls as if they had no mutual attractions. Yes. Let's just check D. Are attracted to the sides of the container and strike the container walls with more force? No. Again, lower pressure means would mean that if they're attracted, more force would mean a greater pressure. Here they're saying you got a lower pressure, so D is absolutely a no. C is correct. Now, guys, there's a lot of examples that I didn't do just because I don't want to make these videos too long. But that's why those practice problems in your homework are really, really important, especially coming back here to this the STP conditions. That 1 mole equaling 22.4 liters. That's going to be really, really helpful. Think about on a multiple choice question where you don't have a calculator. Okay? And they ask you a question about using PV equals nRT, and you're like, well, I can't do this without a calculator. And you're right. I agree. No way. But could you estimate 1.88 times 22.4 and know that, well, 22.4 doubled would be 44.8. So would they expect you to know? It's probably a number a little bit smaller than 44.8. And yes, absolutely yes, that is 100% true. Okay, the exact answer, not a chance. But would they expect you to know? Well, doubling it would be 44.8, so it's going to be a little bit less than that. Yes, absolutely. Okay, and then you could still get that answer for example 3 without using PV equals nRT at all, just using 22.4. Okay, so really focus on those problems in your homework that deal with STP. Make sure you look at the answers, the worked out answers that I've done, and make sure you're understanding how to use that 22.4.